Okay, folks, continuing right along, we're going to talk about some of the commonly occurring electronic transitions in polyatomic molecules. So we haven't spent a whole lot of time in this class talking about characterization like you did in organic chemistry or perhaps even in the analysis series. But I do want to talk just a little bit about a couple commonly occurring transitions that we routinely see in organic and inorganic molecules. So let's flush those out. So the first one that I want to discuss is the pi to pi star and N to pi star transition. So the pi to pi star transition is allowed and readily observed in systems that contain conjugation or even just single pi bonds. And this is spin allowed because we're just going to this simple pi to pi star state. It's on axis, so there will be a very strong Frank-Condon overlap with this to give us a very intense spectrum. So very intense peak from pi to pi star in most, if not all, systems. N to pi star, however, is spin forbidden in most systems. N here refers typically to off-axis electrons that are generally found as lone pairs. And so now comparing these two pictures right away, hopefully you can see that there is not good overlap with this. And for some molecules, this is strictly forbidden. In some molecules, this is observed very weakly. So in most cases, this makes a very weak peak. So these things are like orders of magnitude in difference. So here's one specific example looking at acetone, or really just a carbonyl for that matter. So again, our pi to pi star transition is given by the blue arrow, and an N to pi star arrow might be coming from a non-bonding orbital into the pi star anti-bonding orbital. And here's in the case of acetone, you can see that pi to pi star transition is occurring out near 195 or so. And again, it is a very strong intensity transition. So there is a large amount of absorbance to that transition. However, the N to pi star transition is observed in acetone. That occurs at longer wavelengths, which we might guess just from looking at the energy level diagram. And it occurs at much lower intensity because it is spin forbidden. The asymmetric vibrations of a molecule will occasionally allow this forbidden transition to occur. So that is why we do see it occasionally. And in molecules in which we do see it, N to pi star is great for quantitative analysis because it will occur at a very low absorbance. And so it's occurring within that linear range of Beer's law. Certainly pi to pi star can be used for quantitative analysis as well. But because it occurs at such high intensity, we'd have to dilute our sample or use a very narrow path length to do quantitative stuff with pi to pi star. So just a few more examples showing that. Here we have a series, ethene, butadiene, and hexatriene. And this is to show you what happens as we increase the degree of conjugation. Our HOMO-LUMO gap, or in other words, our pi to pi star gap, gets smaller. And there's a really cool explanation for this. It's something we've talked about already. It is the particle in a box. So we can imagine now in this pi system, here are my walls, and my box is the molecule. And in this pi system, electrons are free to move. And if you recall, when that box was really small, that owes to a really small wavelength that can fit inside the box, which means there's a large energy gap. So now if we look at butadiene, and again, it's important to note that this is for conjugated systems. Our box has gotten bigger. Our electron is free to move throughout this box in this conjugated pi system, and thus the electron, or the gap between the HOMO and LUMO, gets smaller. And then, of course, with hexatriene, it's an even larger box, so it's an even larger wavelength, owing to an even smaller HOMO-LUMO gap. So in this pi to pi star transition, as the box gets bigger, or as our degree of conjugation increases, we would see a red shift of the pi to pi star transition. Okay, so I want to shift and get into a different style of transition. So this pi to pi star and N to pi star, very, very common in organic molecules. And of course, particularly organic molecules with pi bonds, such as carbonyls or olefins or rings that are conjugated and the like. So if we move to inorganic systems, very commonly occurring electronic transitions in polyatomic molecules are given by D to D transitions in metal complexes. And there's 3 of these types that I'm going to go into, and it's all dependent on the type of complex the metal forms. So here is a picture of hexoaqua chromium 3. And if you recall, chromium 3 plus will have 3 free D electrons. It will be a that would be a quadruplet state. I blanked out there for a minute. And so now, based on the structure, those levels, the D levels, will split. And they will split in the following way. In the case of octahedral field splitting, these D orbitals are in close proximity to the bonds of the ligand, the coordinate bonds. And that creates a non-favorable interaction. That's an electron-electron interaction. So the D orbitals that are most closely overlapping with those ligands are split to higher energies. So for example, you can see here in this octahedral crystal structure, the dx squared minus y squared, those orbitals are overlapping or interfering with the coordinate bonds in the ligand. And similarly, the dz squared are also directly overlapping with those. So that causes those to split to higher energy levels. Whereas now the off-axis d orbitals, the dxy, the dyz, and the dxz, hopefully you can see from these pictures, they're not interfering with those ligand coordinate bonds as much. So they are lower in energy than the on-axis bonds. Overall, though, they are still higher in energy due to the electron-electron interaction. So now then, in chromium 3, we will have 3 electrons in this level. And when we use light to stimulate this process, we'll get one of those electrons moving up a level. And that's what owes to this DD transition, which gives us the brilliant color that we associate with complex metal ions. So these give us lovely, visible colors that we're so used to seeing in our complex ions. So there's 2 more of these to discuss that are commonly occurring. So if we have a square planar crystal structure, the splitting will be different. So as we might imagine, the dx squared minus y squared will be in the most contact with the ligand coordinate bonds. So that will give this the highest energy. The dxy is the second highest energy due to its close proximity to the electrons in those ligands. And then the dz squared and the dxz and the dyz will have even lower overlap. So then, of course, finally, the last one to talk about is tetrahedral field splitting. And this ends up being the opposite of the octahedral field splitting. So you can see in the tetrahedral, the dx squared minus y squared and the dz squared will be off axis from the ligand coordinate bonds, whereas the dxy, the dyz, and the dxz will be in close proximity, which is why those split in the way that they do. And of course, we could go into much more detail and talk about why certain complex ions exhibit square planar or tetrahedral or octahedral structures based on this notion. But you will get into that in plenty of detail in inorganic chemistry. The main thing that I wanted to note is these transitions from these splitting DD levels, these give us lovely, brilliant colors in complex ion solutions. Okay, folks, so that was just a brief discussion of commonly occurring electronic transitions in polyatomic molecules. Even though that was very brief, the ones that I discussed here, you will see ad nauseum in your chemistry studies using UV-Vis. Okay, I'll see you in the next video.